today we're going to start talking about the process that we've already kind of built all the foundations of that we need. And this goes by a couple different names. Sometimes you'll see it called differential equations. You'll see it sometimes called initial condition problems. Sometimes it's called an initial value problem. But the idea is that I'm giving you the derivative of the function, and you're going to tell me what the original function was. And we have done this quite a bit, but we're going to add one more piece to it today. So that's what we're going to be looking at. So a lot of this is going to be familiar to you. So an equation involving a derivative is called a differential equation. And that's what we're going to be solving. And there's a whole class that you can take, especially if you're going into like physics and engineering, that is on solving differential equations, because physics involves a lot of rates of change. We've talked about slope fields. Those can give me an idea of the solutions to differential equations, because you saw that if I started at a particular point, then you could start to connect the dots to see what the curve would look like. That's basically what we're going to end up doing, but instead of on a graph, we're going to use our algebra and our calculus. So what we have done so far is using definite integrals. So usually there have been boundaries that we are taking this integral from. Usually we have like an a down here and a b up here. With an indefinite integral, not the case. There's no a and b, and it's just, in general, what is the integral? And so that is going to involve taking our antiderivative, and this is where our plus c is going to come into play. When we first talked about antiderivatives, we talked about how there could be some constant out in front of here. This derivative of a constant is going to be 0. And so now that we don't have these bounds and those plus c's aren't going to cancel, when we take plug in at the top minus plug in at the bottom, now we do need the plus c there. And that's going to be really important for what we're going to do this week. So, indefinite integrals. One thing I'll just point out, one thing we can do that you're going to see happen a lot of the time is that sometimes if there's some messy decimal or big constant that is inside of the integral, if I can factor it out of the whole function, a lot of times you will see people just and problems just take the constant and bring it out in front. And so sometimes you'll see, for example, if we have the integral of 30 natural log of x or something like that, then sometimes you'll see them bring the 30 out in front like this. And these two mean the same thing. And that way we don't have to deal with the 30 anymore. We'll do that a lot more in the next section. But if there's a constant inside of the integral, then we can bring it out in front, is the idea here. And then on the next page, if you're following along in the notes, you should see all of the derivative rules and antiderivative rules. And we've already talked about all these. So here's the power rule. Here's undoing the power rule. Natural log. When we do this with the antiderivatives, we need the absolute value because we can't take the natural log of a negative number. Antiderivative e to the x is e to the x. And then here's all our trig. You should know these already. The only difference is that when we do this, we're going to put a plus c on these. So we're going to get started by practicing and warming up with some antiderivatives here. So if the derivative was 5x to the fourth minus secant squared of x, well, the antiderivative here would be antiderivative of 5x to the fourth. Well, then I must have had an x to the fifth. And what goes out in front of here? Well, just a 1. So it's just x to the fifth. And then minus what function has a derivative of secant squared? That's going to be tangent. And now that I want the general indefinite integral plus c, make sure you have your plus c's out in front of all of these. So that is part A. Don't forget your plus c's. I want you to try parts B and C now on your own. These should all be fairly straightforward antiderivative rules. You shouldn't be doing anything overly complicated on something like part C. This is a derivative rule something. So is this. So I'll give you about 1 minute to do that, and I'll check to make sure during class tomorrow that you have that you have these two down and ready to go. And if we need help on it, then I'll help you on it tomorrow. So I'll give you 1 minute to try these two, and then we'll move on to the next page. All right. Now we have all the tools and foundations we built. So let's look at the actual problems that we're going to be looking at. What these problems are going to involve is that, remember that all of these need to have a plus c out in front. Well, if I tell you a point that's on the graph, we can use that point to solve for c. So in other words, if you want to lay it out in steps, then step number 1 is going to be take the antiderivative. And then step number 2 is going to be use the point that's given to you to solve for c. That's all we're doing here. So we're just adding one extra step to something that we already know how to do. So y equals antiderivative of 3 sine of x. Well, there's going to be a 3 out in front here. Antiderivative of sine is going to be a negative cosine. Right? Because the derivative of cosine would be negative sine. So in order for it to be a positive, it had to start off being negative. Plus c. And now here's the key part of the process that's new, is that we're going to be using the point that they give us to solve for c. So this is step 2 in our process, which is that y is 2 when x is 0. So that means we're going to plug in 2 for y, and we're going to plug in 0 for x, and we're going to solve for c. Cosine of 0. So this is going to get us back with practicing, evaluating things and plugging things in, understanding the relationship between our integrals and derivatives, and hopefully really laying the foundation of these antiderivative rules and getting you solid on them. Oh, let's see. 2 equals negative 3 cosine of 0. Careful, is 1. So 2 equals negative 3 plus c, which, if I add 3 to both sides, is going to mean that c has to be 5. And so our final answer here is going to be y equals negative 3 cosine of x. So our antiderivative function. And now we know that c is 5. And so we're going to put plus 5. That's what we want to put if, indeed, we want the function at 0 to come out to be 2. So we're taking the antiderivative here, and then we're going to plug in the point that they give us to solve for what c is.